Okay, welcome to the morning video. So, I'm going to keep going on this book. The next part is we're going to focus on the network problem identification scenario. So, we've got 500 metrics coming in, and then we're creating them into a function. So here's the function, y equals f of all of these factors here. We aim to find that mathematical approximation to the f of x function. I don't know if it's f of x, because remember, we had conversations with ChatGPT to try to get good at speaking equations out in English, and I don't know if it's better to say f of x or f parentheses x. I know when I was in school that would be said f of x, but I wasn't learning from Richard Feynman, and ChatGPT didn't exist, so the way I learned it in school quite possibly was not the best possible way to learn it. And I feel like now with ChatGPT, although I can do better. So read out loud. Okay, so I'm going to say read this in English. Read this mathematical notation. English. F of x. Okay.
The mathematical notation fx is read in English.
Now tell me more about why the word of is used.
The word of conveys that there is a specific operation or set of operations defined by the function f that is applied to xxx. For instance, if fx equals x2 plus 3f, x equals x squared plus 3f, x equals x2 plus 3, it implies that the function f takes an input xxx, squares it, and then adds 3 to the result. Using of also aligns with common language patterns, making the description more intuitive and accessible. It helps to emphasize that xxx is not just a value, but it is being subjected to the rules or transformations defined by f. Thus, f of x effectively communicates that xxx is being processed through the function f.
Okay. All right. Well, that's fine. So we aim to find that mathematical approximation to the f of x function given those 500 input variables. The machine learning model will represent such an approximation. But how do we obtain this model? It is a classification problem. So let's say we choose a specific algorithm from those adequate for classification. Next, how do we find the parameters in that algorithm that will make it become the approximated function that we need? The process is conceptually simple. Number one, we have an input dataset which consists of n observations, each being a 500 dimension vector, the 500 network metrics we have. Number two, we analyze our algorithm, our model. And we don't analyze it yet. Number two is to initialize the algorithm. So number two is we initialize our algorithm, our model, with a random set of parameters. More on the randomness of the initialization later. Number three, we run these n observations through our initialized model and evaluate the output. With all probability, the output has nothing to do with the answers, labels we expected. Number four, we compute the error. Let's say for now the error is the difference between the predicted labels and the actual labels. Number five, with this error, we recompute the model parameters. Depending on the algorithm, this process will be different, but let's just assume there is some method by which we can produce an updated set of parameters of the model that is expected to produce a smaller quantity of error in next iterations. Number 6, go back to step 3 and repeat until the obtained error is below a certain acceptable threshold. Okay, so this is a description of that. Let's just have ChatGPT talk about this. I think that's generally pretty useful. There was another one on the before to start this off, but that one was pretty straightforward. So let's get an explanation of that and then move on and read more about this.
It looks like you've uploaded an image related to machine learning or statistical modeling. How can I assist you with it?
All right, I need a quick break. I'll be right back. All right, I'm back. So ChatGPT needed a more complete prompt. So let's look back and see if I have something from the book. So here's something where we're talking about mathematical equations. So anything. So here's something about. There we go. So here's something about that. Let's just say, tell me more about the image.
The image you uploaded appears to represent a machine learning model process diagram. Here's a detailed breakdown of its components. Observations. The diagram begins with multiple observations, e.g., observation 1, observation 2, each consisting of a set of input features labeled from x1 x_1 by 1 to x500 x_500 x500. This implies that each observation has 500 features, which are input data points used by the model to make predictions. Model. The core of the diagram is the model, which likely represents a machine learning algorithm. This model takes the input features, data xxx, and attempts to predict an output yyyy. Outputs and targets. For different sets of observations, there are different target values of yyyy, e.g., y equals 2, y equals 2, y equals 2, and y equals 5, y equals 5, y equals 5. These target values are what the model is trying to predict accurately. Iterate and error. The model outputs predictions and these are compared against the true target values. The difference, termed as error, is used to refine and improve the model through an iterative process. The cycle of prediction, error calculation, and model updating typically continues until the model achieves a satisfactory level of accuracy or a set number of iterations is reached. This type of diagram is common in explaining supervised learning models where the goal is to train models so that it can make accurate predictions on new, unseen data, based on the learning from the training data, i.e., the observations with known target values. The process emphasizes the cyclical nature of model training, including forward passes, predictions, and backward passes, updates based on error.
Okay, so there was a influencer. Here we go. Yeah, so Zain Khan is kind of doing a good job at being a effective influencer online, and he's doing it in the field of AI, which is a little bit kind of I feel like anyways, so he has a post. He has like these cheat sheets that are pretty good. So there's like, it's like act as a blank, something blank. So he has it for specific things. There was like a really good one. I wish I had bookmarked it. Maybe I did under hobbies information. I should have bookmarked it under here. Anyways, I guess I'm satisfied. So let's move on. There's a great deal of simplification in the above workflow, but I think this level of detail is enough for now to understand how the training process works. With this iterative workflow, we are training our model to be better at producing the answers we want, labels, given the data we have. You may have heard the saying, experience is the accumulation of your past errors. This is essentially what is happening here. We are bringing the experience to the model by forcing it to make errors. The process of making errors guides the model to adapt and evolve, by updating its parameters in the direction where the errors become lower and lower, ideally to the point that the results are acceptable enough for our goal. At that point, the training process ends and the model is ready to be used. It is fit. Some additional remarks are useful, though, to better understand the workflow above. About the random initialization. In most of the algorithms, the parameters will be randomly initialized, but how they are initialized will matter to the result. So, frequently, the algorithm implementations will allow you to control such initialization, but generally, the parameters will be initialized to some random value. You do not know where the model starts, but there is some expectation around where the model ends after this training process. About the error. The error is not the difference. Most of the time, there will be an error function that will characterize the deviation between the actual and predicted labels. Depending on the type of problem, the function will be different. However, conceptually speaking, I want you to understand that the error captures the difference or deviation between the expected and actual results. So it's not always the difference. It can be the deviation. If it's a negative difference, then it's a sum, I guess. About the parameter model recomputation. This is very much algorithm specific, and I will give you some more insights as we describe some of the algorithms in detail. Just assume for now that there is a mathematical way to update by a certain amount the model parameters based on the computed error, and that such an update usually, hopefully, happens in the direction that will lower the error in the next iteration. About repeating the process. I've stated that we iterate and repeat the process until it converges to an error value below an acceptable threshold. There is no guarantee, however, that this will happen. There is no guarantee at all. We start this process based on certain assumptions that our data will allow us to train this model, but this may not be the case, and our training workflow may never converge or produce the desired results. Why is that? It could be a data problem, an algorithm choice problem, a hyperparameter choice problem, or a parameter initialization problem. There are many reasons why a training process may go nowhere. This is why I was referring to machine learning in some sense. This is why I was referring to machine learning in some sense, and I should say as an art, because there is a lot of trial and error. Experience will bring some level of intuition of what may or may not work in many cases. Most of the time, there is no deterministic way to know in advance if this combination of decisions or assumptions you've taken to train this model is correct, wrong, or optimal. Because of this, the process may need to be repeated many times. Sometimes because it may not converge at all. Other times because you need to find the optimal model for your use case, and trial and error iteration is required. Auto machine learning techniques to help here. Again, let's remember, brute force is your friend, and that's kind of the key things that computers can do. They can just sit and calculate things, 24/7. So, about the N observations in your dataset. In my oversimplification of the reality, I said in step 3 you run your N observations through the model. That is not precisely accurate. If you have n observations, you will likely split them into at least two buckets: training and testing. All right, and I remember this from the Fast AI course. Basically, what you want to do is preserve some of your data so you can validate the results. So we can see that total data set gets divided into two parts, one part for training and one part for testing. And you don't need to use half and half for each. You just need a small part that mathematically will produce a valid test. You don't need to use all your data for that. You don't need to even use half of it. You just need to use the mathematically relevant ratio. A portion of our data set will be used to train our model. To train our model, these observations will be pushed many times. Every pass through the training set is referred to as an epoch. However, we should not use the same samples to test how well or badly our model behaves once we finish our training. Our goal is not to make the model work well for our dataset. Our goal is to make the model work well for our use case. Our dataset is only a hopefully good representation of our use case. And this is where there's classic ethical considerations. For example, police departments in the United States would use AI products that are trained on data sets that aren't fair, where the result is they identify potential suspects based on a set of characteristics that real suspects don't necessarily have. So now whenever there's a crime, they go after suspects that match the result of their AI tool, but their AI tool was trained on data that doesn't reflect the real world. So now they're always trying to put an innocent person away. I mean, not always. This is just an example of how this might go wrong. And I'm using this as an example because it's the classic example that's given. This is the example you'll see a lot in textbooks. I follow Rachel Thomas and Fast AI Learning, Jeremy Howard. It's the example they give. I might not have repeated it back in the exact perfect way, but if you go on to learn about this more, this concept of having a hopefully, in quotes, a good representation of our use case is where the ethics of AI can have like real, the meat of AI can be unethical, comes from the data set in a lot of cases, and that's not just the only way where AI can be unethical and unaligned and cause more problems than it solves, but it's definitely a big one. That data has to be valid to the use case, otherwise there are going to be big problems. Therefore, we need to keep a portion of our data set reserved for testing. We must evaluate how our trained model performs with data not seen during training. There are more nuances to this that I will explain in the next section. But for now, just keep in mind that we will use part of our data set for training and part for testing. How much? As a ballpark number, if the number of observations is in the order of thousands or tens of thousands, the training set will be around 75% to 80% of the total data set, and the testing 20 to 25%. So like an 80-20 division there. There are use cases where we have millions of observations or even more. In those scenarios, a 95% to the production data and a 5% to the training data split may be good enough to test those results, because this 5% is going to constitute a much larger number than if the overall number was lower. Key takeaway. It's all about finding that nonlinear function that approximates the problem you want to solve. Some people will argue it is nothing but a function with tens of millions of if-then-else statements. Probably they are right. Alright, so the next section is overfitting, the never-ending battle. Overfitting is one of the most frequent phenomena in our training model process, and I will dedicate a section to it. It applies to all techniques and algorithms, so I will keep the description to be algorithm agnostic. Let me start by emphasizing that the goal of training a machine learning model, or for that matter, for the overall machine learning project, is not to fit into the training data. It is to solve a real problem. The training dataset available is only a proxy to capture such a real problem. In this context, when you train your model with your training dataset, basically three things happen. Number one, your model does not work well with your training data. We will explain later on the reasons why this may happen. We refer to this as underfitting. Your model is not capturing the patterns in your data, so that function you get produces meaningless results. Number two, your model works very well with your training data, but does not work well with new data / data it has not seen yet. We refer to this as overfitting. Somehow the model is learning the data itself, not just the internal patterns, but also the noise that may be associated with the training data set. We could simplify and say the model is memorizing your data, and then when it is presented with new data, it does not know how to generalize. It memorized, but it did not learn. And that's something human intelligence can do too. Number three, your model works well with both your training and your testing data. That means the model is truly learning the patterns in the data, what is usually referred to as the dark knowledge. This is the goal for any model training process. And I don't like that word dark in there because it makes it sound like it's the bad knowledge, the evil knowledge, like the dark magic, the dark arts, from Harry Potter. So I think a better word would be like the deep knowledge, the hidden knowledge. This is when your model is working well. It discovered some hidden insight in the data that applies to new data. So so I would love to get an example of this. So let's go to ChatGPT and get an example of this. So we'll paste in two things into ChatGPT. So the first thing is this, and then the second thing is these graphs here. So we've got the high bias model. So this is your model does not capture the patterns in your data. The model is too simple. This is called underfitting. So you can see there's none of the patterns here have been captured. Then we've got the optimal model. Your model is learning the patterns in the data. Dark knowledge, I would also call hidden insights, deep knowledge would be better. I don't like that word dark. It just makes it confusing as to what's actually happening. Likely the model complexity is adequate to the type and volume of data. So we can see the data kind of looks like it's curved a bit. So we've got a curved line representing the data, which is much more accurate than a straight line, which doesn't capture this curve at all. And then we've got a high variance model. Your data is learning the data itself, memorizing, not the patterns. Likely the model is too complex. This is called overfitting. So if you've got a new data point, it's hard to know where it actually would be. Here, if you make a prediction that it'll be somewhere on this line, it'll be a lot more accurate. So let me grab a screenshot of this and put that into ChatGPT. Okay, hear what it has to say.
It looks like you've uploaded an image depicting different types of models in machine learning: high bias, optimal, and high variance models. These diagrams are often used to illustrate concepts like underfitting, optimal fitting, and overfitting. High bias model. This model is too simple, which means it does not capture the patterns in the data well. This situation is referred to as underfitting. Optimal model. This model has the right level of complexity to effectively learn the general patterns in the data without being too simplistic or too detailed. Is what one aims for in model training. High variance model. This model is too complex, capturing not just the underlying patterns but also noise in the data. This is called overfitting. The code you provided discusses the idea of model learning the real patterns in the data, sometimes called dark knowledge. This is typically what one strives for, where the model is complex enough to learn the essential patterns but not so complex that it starts to memorize noise. If you have any specific questions about these concepts or need further explanations, feel free to ask.
Okay, so the first question I have is, I don't really like that term dark knowledge because it makes it sound like, oh, it's like dark magic, or like, oh, yeah, like it's kind of like not the best term. I feel like a better term would be like deep knowledge or hidden knowledge, or like the insight, or like something like that. So like, do I have to get used to using the term dark knowledge regardless? Like, it seems like that's an accepted, widely used industry term. So like, if that's the case, like, how can I make this more intuitive and like feel like it's the right term to use? I guess in my own mind, I would think like dark matter is like a way I could think of it that way. So where it seems like it's more or less the correct term, even though my own intuition would think that there'd be a better way to name it.
The term dark knowledge isn't as widely established or mandatory in the field of machine learning as you might think.
Oh, it isn't? Okay, good. I do see it here.
It's one of many informal terms used to describe aspects of model training and the insights that models gain, which aren't immediately apparent just by looking at the model's parameters or outputs. The term tries to evoke the idea of knowledge that is there but not directly visible, much like dark matter in physics.
Yeah.
Your intuition to seek alternative terms like deep knowledge, hidden knowledge, or the insight is perfectly valid and might resonate better with your understanding or the audiences you communicate with. These terms can be more descriptive and less metaphorical, which might help make the concept clearer or more approachable. In machine learning and many other fields, terminology can vary widely between communities, and new terms can gain popularity if they are found to be more descriptive or apt. You could certainly introduce and use terms you find more intuitive when discussing or teaching these concepts, as long as you clarify what they correspond to in more commonly accepted terminology.
Okay, so create a map of the communities in machine learning AI, and like an overview of the communities that exist in this space, and then assign a probability that each community will use the term dark knowledge rather than some other sort of term.
Creating a map of the machine learning and AI communities, along with an overview and an estimation of how likely each community is to use specific terminology such as dark knowledge, involves both identifying these communities and understanding their linguistic preferences. Here's a rough breakdown of some key communities within the field of AI and machine learning. 1. Academic researchers focus, theory, experiments, and pushing the boundaries of what machine learning models can do. Likelihood of using dark knowledge, low and moderate. Academic researchers often prefer precise, descriptive terminology. They might use implicit knowledge, model capacity, or representational power. 2. Industry professionals focus, application of machine learning models to solve real-world problems, often at scale. Likelihood of using dark knowledge, moderate. Professionals might use a variety of terms depending on their background and the influence of academic research in their work. They often favor terms that align with industry standards or that facilitate clear communication with stakeholders. 3. Open source contributors focus, development of tools, libraries, and frameworks that support machine learning. Likelihood of using dark knowledge, low. Contributors to tools like TensorFlow, PyTorch, etc. usually stick to technical and widely accepted terminology to keep communication clear and consistent across diverse global users. 4. AI ethicists and policymakers focus.
Yeah, so I like this. So I am reading a book written by somebody who's providing education, who's creating content in this book. So yeah, there's a good chance that they would use the dark matter term. I don't really like that term. I kind of want to hear about this in other terms. So a good thing for me to do next might be to go and listen to some more AI ethicists and policymakers. So list for me the top 10 AI ethicists and policymakers that exist in the world today.
As of 2024, there are several notable figures in the field of AI ethics and policy who have significantly influenced how we think about the ethical implications and governance of artificial intelligence. Here are 10 of the most recognized and influential AI ethicists and policymakers. Timnit Gebru, a computer scientist and co-founder of Black and AI. She has worked extensively on algorithmic bias and the ethical implications of automated systems. Joy Buolamwini, founder of the Algorithmic Justice League. She is known for her research on facial recognition technology and the social implications of AI, particularly racial and gender bias in algorithms. Kate Crawford, a senior principal researcher at Microsoft Research and co-founder of the AI Now Institute. She focuses on the social and political implications of artificial intelligence. Ruha Benjamin, a professor at Princeton University. She explores the intersection of race, justice, and technology, offering deep insights into the social dimensions of AI and automation. Cathy O'Neil, author of Weapons of Mass Destruction. She is a data scientist and activist known for...
Okay, so I don't need to do any of this more. These are the least likely to use that sort of language, so I might get kind of different terms. So I'm gonna add all of these on LinkedIn, and some of these I recognize. I've seen this person before. I've watched some of their interviews online, so I'm glad I'm following them now. So this is what I'm going to do is follow each of the leading ethicists in AI that are likely to use different terms than I'm seeing in this book. So I get a wide view. I get to see from an educator's and a content creator's perspective, and also from a policymaker and ethicist's perspective as well. Okay, so I think this is CEO at Teaming. So this is let's see if this is the right person. So the person I'm looking for wrote a book. Okay, I think this person probably doesn't have LinkedIn. I don't think this is the same person. So I'm not going to follow this person. Yeah, I'm not going to follow this person. I don't think this is the author of that book. Okay, so this is the right person. The responsible artificial intelligence. Perfect. On a council. So this person, okay, yeah, I can follow them. Good. Some people don't always have the ability to follow turned on. All right, so next person. This is the AI Now Institute. So probably they don't all have it. So this is the person, I think, but I don't think, which is kind of funny that somebody. Yeah, I don't think this person has LinkedIn, but she does appear in some of these posts. So I might want to follow someone who's putting out content. Yeah, so I guess I can follow Michael Bolton, maybe not the singer, because he seems to be putting out high quality posts about leaders in the field, so I would be happy to see those. I like that. Okay, so I'll just follow him just because he's putting out, she doesn't have LinkedIn, and he's putting out content about her, so That's probably good enough, hopefully. Okay, follow this person, and now one more person to follow. And I definitely have to cut it at the 55 mark, no matter where I am. So, we got one more person here, computer science at Berkeley. So, yep, this is the person here. So, follow. There we go. And yeah, so there's a primary factor. Oh, so I'll advance the bookmark. Yep, and I can't get any further. I'm out of time. So when I come back, we'll read about the primary factor that influences whether your model is underfitting, overfitting, or whether you've discovered the secret dark knowledge. So I will delete the past bookmarks. There we go. Close the bookmark tab. And when I come back, we'll learn about the primary factor that includes the usefulness of the model. So thanks for watching, and see you in the next one.